Space Shuttle abort modes were procedures by which the nominal launch of the NASA Space Shuttle could be terminated. A pad abort occurred after ignition of the shuttle's main engines but prior to liftoff. An abort during ascent that would result in the orbiter returning to a runway to a lower-than-planned orbit was called an intact abort, while an abort in which the orbiter would be unable to reach a runway, or any abort involving the failure of more than one main engine, was called a contingency abort. Crew bailout was still possible in some situations where the orbiter could not land on a runway. Redundant set launch sequencer abort. The three Space Shuttle main engines were ignited roughly 6.6 seconds before liftoff, and computers monitored the performance as they built up thrust. If an anomaly was detected, the engines would be shut down automatically and the countdown terminated before ignition of the solid rocket boosters at T0 seconds. This was called a redundant set launch sequencer abort, and happened 5 times: SDS-41D, SDS-51F, SDS-51, SDS-55, and SDS-68. Ascent abort modes. Once the shuttle's SRBs were ignited, the vehicle was committed to liftoff. If an event requiring an abort happened after SRB ignition, it was not possible to begin the abort until after SRB burnout and separation about 2 minutes after launch. There were 5 abort modes available during ascent, divided into the categories of intact aborts and contingency aborts. The choice of abort mode depended on how urgent the situation was, and what emergency landing site could be reached. The abort modes covered a wide range of potential problems, but the most commonly expected problem was a Space Shuttle main engine failure, causing the vehicle to have insufficient thrust to achieve its planned orbit. Other possible non-engine failures necessitating an abort included a multiple auxiliary power unit failure, a cabin leak, and an external tank leak. Intact abort modes. There were 4 intact abort modes for the Space Shuttle. Intact aborts were designed to provide a safe return of the orbiter to a planned landing site or to a lower orbit than planned for the mission. Return to launch site. Return to launch site was the first abort mode available, and could be selected just after SRB jettison. The shuttle would continue downrange to burn excess propellant, as well as pitch up to maintain vertical speed in aborts with an SSME failure. After burning sufficient propellant, the vehicle would pitch all the way around and begin thrusting back towards the launch site. This maneuver was called the powered pitch around, and was timed to ensure less than 2% propellant remained in the external tank by the time the shuttle's trajectory brought it back to the Kennedy Space Center. Additionally, the shuttle's OMS and reaction control system motors would continuously thrust to burn off excess OMS propellant to reduce landing weight and adjust the orbiter's center of gravity. Just before main engine cutoff, the orbiter would be commanded to pitch nose down to ensure proper orientation for external tank jettison, since aerodynamic forces would otherwise cause the tank to collide with the orbiter. The SSMEs would cut off, and the tank would be jettisoned as the orbiter used its RCS to increase separation. Once the orbiter cleared the tank, it would make a normal gliding landing about 25 minutes after liftoff. Should the second SSME have failed at any point during PPA, the shuttle would not have been able to make it back to the runway at KSC, but the crew would be able to bail out. A failure of a third engine during the PPA maneuver would have led to loss of control and subsequent loss of crew and vehicle. Failure of all 3 engines as horizontal velocity approached zero just before external tank jettison would have also resulted in LOCV. The capsule communicator would call out the point in the ascent at which an RTLS was no longer possible as negative return. approximately 4 minutes after liftoff, at which the vehicle would be unable to safely bleed off the velocity it had gained in the distance between its position downrange and the launch site. This abort mode was never needed in the history of the shuttle program. Astronaut Mike Mullen referred to the RTLS abort as an unnatural act of physics, and many pilot-astronauts hoped that they would not have to perform such an abort due to its difficulty. Transoceanic abort landing. A transoceanic abort landing involved landing at a predetermined location in Africa or Western Europe about 25 to 30 minutes after liftoff. It was to be used when velocity, altitude, and distance downrange did not allow return to the launch point via RTLS. It was also to be used when a less time-critical failure did not require the faster but more dangerous RTLS abort. A TAL abort would have been declared between roughly T+2 30 minutes and main engine cut-off about T+8 30 minutes. The shuttle would then have landed at a designated airstrip across the Atlantic. The last 4 TAL sites were Istres Air Base in France, Zaragoza and Morand Air Bases in Spain, and RAF Fairford in England. Prior to a shuttle launch, 2 sites would be selected based on the flight plan, and were staffed with standby personnel in case they were used. The list of TAL sites changed over time and depended on orbital inclination. Preparations of TAL sites took 4 to 5 days and began 1 week before launch, with the majority of personnel from NASA, the Department of Defense and contractors arriving 48 hours before launch. Additionally, 2 C-130 aircraft from the Manned Space Flight Support Office from the adjacent Patrick Air Force Base, delivering 8 crew members, 9 pararescuers, 2 flight surgeons, a nurse, a medical technician, and 2,500 pounds of medical equipment to either Zaragoza, Istres, or both. 1 or more C-21S or C-12S aircraft would also be deployed to provide weather reconnaissance in the event of an abort, with a TALCOM, or astronaut flight controller, aboard for communications with the shuttle pilot and commander. This abort mode was never needed during the entire history of the Space Shuttle program. Abort once around. An abort once around was available if the shuttle was unable to reach a stable orbit but had sufficient velocity to circle the Earth once and land, about 90 minutes after liftoff. The time window for using the AOA abort was very short, just a few seconds between the TAL and ATO abort opportunities. Therefore, taking this option was very unlikely. This abort mode was never needed during the entire history of the Space Shuttle program. Abort to orbit. An abort to orbit was available when the intended orbit could not be reached but a lower stable orbit was possible. This occurred on mission SDS-51F, which continued despite the abort to a lower orbit. The Mission Control Center in Houston, Texas, observed an SSME failure and called Challenger Houston abort ATO. The moment at which an ATO became possible was referred to as the press to ATO moment. In an ATO situation, the spacecraft commander rotated the cockpit abort in mode switch to the ATO position and depressed the abort push button. This initiated the flight control software routines which handled the abort. In the event of a loss of communications, the spacecraft commander could have made the abort decision and taken action independently. A hydrogen fuel leak in one of the SSMEs on SDS-93 resulted in a slight underspeed at MECO, but was not an ATO, and the shuttle achieved its planned orbit. If the leak had been more severe, it might have necessitated an ATO, RTLS, or TAL abort. Preferences. There was an order of preference for abort modes. ATO was the preferred abort option whenever possible. TAL was the preferred abort option if the vehicle had not yet reached a speed permitting the ATO option. AOA would have been only used in the brief window between TAL and ATO options, or if a time-critical emergency developed after the end of the TAL window. RTLS resulted in the quickest landing of all abort options, but was considered the riskiest abort. Therefore, it would have been selected only in cases where the developing emergency was so time-critical that the other aborts were not feasible, or in cases where the vehicle had insufficient energy to perform the other aborts. Unlike all previous United States crew vehicles, the shuttle was never flown without astronauts aboard. To provide an incremental non-orbital test, NASA considered making the first mission an RTLS abort. However, SDS-1 Commander John Young declined, saying, "Let's not practice Russian roulette." Contingency aborts. Contingency aborts involved failure of more than one SSME and would generally have left the orbiter unable to reach a runway. These aborts were intended to ensure the survival of the orbiter long enough for the crew to bail out. Loss of two engines would have generally been survivable by using the remaining engine to optimize the orbiter's trajectory so as to not exceed structural limits during re-entry. Loss of three engines could have been survivable outside of certain black zones, where the orbiter would have failed before bailout was possible. These contingency aborts were added after the destruction of Challenger. Post-Challenger abort enhancements. Before the Challenger disaster during SDS-51L, Ascent abort options involving failure of more than one SSME were very limited. While failure of a single SSME was survivable throughout descent, failure of a second SSME prior to about 350 seconds would mean an LOCV, since no bailout option existed. Studies showed that an ocean ditching was not survivable. Furthermore, the loss of a second SSME during an RTLS abort would have caused an LOCV except for the period of time just prior to MECO, as would a triple SSME failure at any point during an RTLS abort. After the loss of Challenger in SDS-51L, numerous abort enhancements were added. With those enhancements, the loss of two SSMEs was now survivable for the crew throughout the entire ascent, and the vehicle could survive and land for large portions of the ascent. The struts attaching the orbiter to the external tank were strengthened to better endure a multiple SSME failure during SRB flight. Loss of three SSMEs was survivable for the crew for most of the ascent, although survival in the event of three failed SSMEs before T+90 seconds was unlikely due to design loads being exceeded on the forward orbiter (ET) and SRB (ET) attach points, and still problematic at any time during SRB flight due to controllability during staging. A particular significant enhancement was bailout capability. Unlike the ejection seat in a fighter plane, the shuttle had an in-flight crew escape system. The vehicle was put in a stable glide on autopilot, the hatch was blown, and the crew slid out a pole to clear the orbiter's left wing. They would then parachute to Earth or the sea. While this at first appeared only usable under rare conditions, there were many failure modes where reaching an emergency landing site was not possible, yet the vehicle was still intact and under control. Before the Challenger disaster, this almost happened on SDS-51F when a single SSME failed at about T+345 seconds. The orbiter in that case was also Challenger. A second SSME almost failed due to a spurious temperature reading, however the engine shutdown was inhibited by a quick-thinking flight controller. If the second SSME had failed within about 69 seconds of the first, there would have been insufficient energy to cross the Atlantic. Without bailout capability, the entire crew would have been killed. After the loss of Challenger, those types of failures were made survivable. To facilitate high-altitude bailouts, a crew began wearing the launch entry suit and later the advanced crew escape suit during ascent and descent. Before the Challenger disaster, crews for operational missions wore only fabric flight suits. Another post-Challenger enhancement was the addition of East Coast abort landings. High-inclination launches were now able to reach an emergency runway on the east coast of the United States under certain conditions. An Ecl Abort was similar to RTLS, but instead of landing at the Kennedy Space Center, the orbiter would attempt to land at another site along the east coast of North America. Various emergency landing sites extended from South Carolina and Bermuda up into Newfoundland, Canada. Ecl was a contingency abort that was less desirable than an intact abort, primarily because there was so little time to choose the landing site and prepare for the orbiter's arrival. The Ecl emergency sites were not as well equipped to accommodate an orbiter landing as those prepared for an RTLS abort. Numerous other abort refinements were added, mainly involving improved software for managing vehicle energy in various abort scenarios. These enabled a greater chance of reaching an emergency runway for various SSME failure scenarios. Ejection escape systems. An ejection escape system, sometimes called a launch escape system, had been discussed many times for the shuttle. After the Challenger and Columbia losses, great interest was expressed in this. All previous U.S. manned space vehicles had launch escape systems, although none were ever used. Ejection seat. The first two shuttles, Enterprise and Columbia, were built with ejection seats. It was only these two that were planned to be flown with a crew of two. Subsequent shuttles were built only for missions with a crew of more than two, including seats in the lower deck, and ejection seat options were deemed to be infeasible, so Challenger, Discovery, Atlantis, and Endeavour were built with no ejection seats. The type used on the first two shuttles were modified versions of the seats used in the Lockheed State Route 71. The approach and landing tests flown by Enterprise had these as an escape option, and the first 4 flights of Columbia had this option as well. But SDS-5 was the first mission to have a crew of more than 2, and the commander made the decision that the ethical thing to do was to fly with the ejection seats disabled. Columbia's next flight was likewise flown with the seats disabled. By the time Columbia flew again, it had been through a full maintenance overhaul at Palmdale and the ejection seats had been fully removed. Ejection seats were not further developed for the shuttle for several reasons. Very difficult to eject 7 crew members when 3 or 4 were on the middeck, surrounded by substantial vehicle structure. Limited ejection envelope. Ejection seats only work up to about 3,400 miles per hour and 130,000 feet. That constituted a very limited portion of the shuttle's operating envelope, about the first 100 seconds of the 510 seconds powered ascent. No help during a Columbia-type re-entry accident. Ejecting during an atmospheric re-entry accident would have been fatal due to the high temperatures and wind blast at high Mach speeds. Astronauts were skeptical of the ejection seat's usefulness. SDS-1 pilot Robert Crippen stated, "In truth, if you had to use them while the solids were there, I don't believe you'd. If you popped out and then went down through the fire trail that's behind the solids, that you would have ever survived. Or if you did, you wouldn't have a parachute, because it would have been burned up in the process. But by the time the solids had burned out, you were up to too high an altitude to use it." so I personally didn't feel that the ejection seats were really going to help us out if we really ran into a contingency. The Soviet shuttle Buran was planned to be fitted with the crew emergency escape system, which would have included K-36RB seats and the Strige full-pressure suit qualified for altitudes up to 30,000 meters and speeds up to Mach 3. Buran flew only once in fully automated mode without a crew, thus the seats were never installed and were never tested in real human spaceflight. Ejection Capsule, an alternative to ejection seats, was an escape crew capsule, a cabin escape system where the crew ejected in protective capsules, or the entire cabin is ejected. Such systems have been used on several military aircraft. The B-58 Hustler and XB-70 Valkyrie used capsule ejection, while the General Dynamics F-111 and early prototypes of the Rockwell B-1 Lancer used cabin ejection. Like ejection seats, capsule ejection for the shuttle would have been difficult because no easy way existed to exit the vehicle. Several crew members sat in the middeck, surrounded by substantial vehicle structure. Cabin ejection would work for a much larger portion of the flight envelope than ejection seats, as the crew would be protected from temperature, wind blast, and lack of oxygen or vacuum. In theory, an ejection cabin could have been designed to withstand re-entry, although that would entail additional cost, weight and complexity. Cabin ejection was not pursued for several reasons. Major modifications required a shuttle, likely taking several years. During much of the period the vehicle would be unavailable. Cabin ejection systems are heavy, thus incurring a significant payload penalty. Cabin ejection systems are much more complex than ejection seats. They require devices to cut cables and conduits connecting the cabin and fuselage. The cabin must have aerodynamic stabilization devices to avoid tumbling after ejection. The large cabin weight mandates a very large parachute, with a more complex extraction sequence. Airbags must deploy beneath the cabin to cushion impact to provide flotation. To make on-the-pad ejections feasible, the separation rockets would have to be quite large. In short, many complex things must happen in a specific timed sequence for cabin ejection to be successful, and in a situation where the vehicle might be disintegrating, if the airframe twisted or warped, thus preventing cabin separation, or debris damaged the landing airbags, stabilization, or any other cabin system, the occupants would likely not survive. Added risk due to many large pyrotechnic devices. Even if not needed, the many explosive devices needed to separate the cabin entail some risk of premature or uncommanded detonation. Cabin ejection is much more difficult, expensive and risky to retrofit on a vehicle not initially designed for it. If the shuttle was initially designed with a cabin escape system, that might have been more feasible. Cabin capsule ejection systems have a patchy success record, likely because of the complexity. Space Shuttle Abort history. Source: